All right, so we're going to talk about today bitwise operators and bitwise operations. That'll be the first half of this set of slides. We'll do the next one, next half next time. Yeah, we're going to work with individual bits of numbers finally. So you have to remember binary, all right? So yeah, bitwise operators is manipulated by bitwise operations. I'm going to be teaching you about that. So remember what a bit is? Like here's a byte, 10110110. 8 bits make a byte, and we're going to make a program, or several programs, that can manipulate individual bits. Like they can check, hey, is this a bit, a 1 or a 0? And if it's not, let me flip it. Let me make it a 1. Let me make it a 0. I'll show you how to do all that. I'll show you how to interact with numbers in their binary form, bitwise. All right, so let's remember binary first of all, because we have to think about that when we perform bitwise operations, because all these bitwise operators, they work on the bits of a binary number. A bit is just a 0 or a 1, right? And do you remember how to expand all these numbers? Like if I gave you 10011 in binary, could you convert that to decimal again? You have to do that base expansion. Like this is the 2 to the 0's place, 2 to the 1's place, 2 to the 2's place, 2 to the 3's place, 2 to the 4's place. This is going to be 1 times 2 to the 4 plus 1 times 2 to the 1 plus 1 times 2 to the 0, which adds up to 19. And so let's just do a simpler one, 1011. Binary, that's equal to, right? You usually start from the right. This is 2 to the 0's place, 1 times 2 to the 0 plus another 1. 1 times 2 to the 1 plus, I don't really need to count this one, but I will anyway. 0 times 2 squared plus, finally, 1 times 2 cubed. Right? Add them all together, that's 8 plus 0 plus 2 plus 1, so that is 11. So this number, 1011 binary, was 11 in decimal. Okay, so any questions about that? Do you remember that? Hopefully. Okay, so yeah. The number 0 is just a bunch of zeros. Like we have 32-bit numbers inside of an int. It's just 32 ints. If you have the number 0, it's just 32 zeros in a row. Boop, 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 all the way. 32 of them. 32 zeros in the int 0. Because ints take up 32 bytes. 0 is stored as nothing but zeros. So you can have leading zeros. That's what I'm trying to say there. And then also, we've only been talking about positive numbers in binary up to this point. Like we know that 1 is a bunch of zeros and a 1. We know that 2 is a bunch of zeros and then 1 0, right? But how do we store like negative 1? We'll talk about that. But it's 32 bits total. If you're making a number, it takes up 32 bits if you're storing it in an int. So you might have to pad left with some zeros, for example. Like 4 is 1 0 0 with a bunch of zeros this way. You've got to fill 32 bits. Okay? Does that make enough sense? That's how our numbers are stored, at least in int land. And I guess for my first trick, I want to show you how negative numbers are stored inside of a computer. I haven't really thought about that, because it's got to be binary. At the end of the day, everything needs to get down into ones and zeros. How in the world do we store negative numbers with a bunch of ones and zeros? So we can actually derive what negative 1 should be, and then I'll show you the general pattern. It'll be fun. So yeah, whatever, think about it. Whatever negative 1 in 32-bit is, whatever negative 1 is in an int amount of space, if we add that thing to to 1, right, and it's supposed to be negative 1, we should end up with 0, right? That's what negative 1 is supposed to do. Get rid of a 1, make the whole thing 0. We know what 0 looks like. It's just all zeros. So that's how we can derive what negative 1 should be. Ooh. So let's pretend we're working with 4-bit numbers, because I don't want to write 32 bits at a time. Here is the number 1. Right? Here's the number 1 in binary. Let's pretend we only have 4 bits in our numbers instead of 32 bits. They're just 4-bit numbers only. I need to come up with the 4-bit representation of negative 1. And I know what it should be, right? Because if I add in binary land, I should end up with zeros. That's the number 0. So -1 plus 1 should make 0. So if I can figure out what should be up here, I have made -1. Okay? So let's discover what it needs to be. So I guess let's start from the right. This bit, first of all, it cannot be 0. Whatever -1 looks like, its rightmost bit cannot be 0 because that would make this a 1, right? I don't want it to be a 1. I want it to be 0. So that's kind of like forced our hand. This is now a 1. All right? And that also makes us carry, right? If you're adding binary numbers, 1 plus 1 is 2, which is 1, 0. So we're carrying to the next place. So again, look at what's going on. I have to add these, right? Plus this question mark. If I let this be a 0, 1 plus 0 plus 0 would make a 1 here. I don't want a 1 here. I want it to be -1 and cancel everything out. So I'm again forced to put a 1 here. The second to rightmost bit of -1 must be a 1. And again, we have to carry. 1 plus 1 is 1, 0. Carry the 1. And we're in the same situation. I can't put a 0 here because I get a 1. I want a 0. So I need to have a 1. And again, we carry. I'm forced to, again, put a 1 here so I get a 0. And then we also carry one last time, but we're pretending our numbers only fit in 4 bits. You can imagine this also works in 32-bit land. You don't have a 33rd bit to put anything anywhere. We don't have a 5th bit to put anything anywhere. And so it just kind of vanishes off in the ether. That's how it works. We just forget about that bit. And look at what happened. We have noticed that 1, 1, 1, 1 must be -1. That's equal to -1. And you can extrapolate this in 32-bit land. -1 in that is going to be all 1s again. It's just going to be 32 1s this time, because that's how many bits you have room for. Okay? Are there any questions about that? 1, 1, 1, 1 is -1. It's the binary number with all 1s. That is -1, because when you add it to 1, you get 0. That's how you do it. But it's also 15, right? 1 plus 1 plus 1 plus 1. If you think about that normal binary, it's like 8 plus 4 plus 2 plus 1, also 15. So we have thrown away the ability to represent 15. Oops, sorry. We've thrown away the ability to represent some large numbers by including negative numbers. And your book might have talked to you about that already. Like unsigned ints, you can store bigger numbers than just normal ints, because you're saving some room for negatives. All right, so yeah. The reason this works is because that final carry, when we're adding numbers, it doesn't do anything. It just vanishes. All right, there's no 33rd bit. There's no 5th bit. Okay, let's do the same to discover what -2 should be. So here is whatever -2 is in binary. It should be added to 2. This is +2 in binary, right? And it should make 0, right? -2 plus 2 should make 0. So we need to get a bunch of zeros. Let's derive what -2 must be. Well, I can't put a 1 here for once. So this part needs to be a 0. I can't put a 0 here because that would make it a 1 down here. So this better be a 1. And now I have the same issue that I had with -1. And so I have a carry here. Can't put a 0. Better put a 1. Another carry. Same situation. Better put a 1. That ending carry 1 vanishes. We don't have extra space for it. Right? So that gives me all zeros. So that means 1, 1, 1, 0, at least in 4-bit land, is -2. It's equivalent, let's say, instead of equal. -2. All right? That is the idea. Any questions about that? So you can do this long process if you want to for any number and discover what the negative version of it should be. And the technical term for all of this, the fancy form that we've just discovered for negative numbers, is called 2's complement. That's how we say this. That's how we store numbers that are negative in a computer. We call it 2's complement form. And there's a trick to do it quickly, to negate any binary number. All right, to negate a number, all you have to do, and you don't have to do this fancy derivation ever again, all you have to do is flip all the bits of that number. So 1s become 0s, 0s become 1s, and then you add 1 to it. Okay? So for example, doing this to +1 will turn into -1. So start with positive 1, 0, 0, 0, 1, flip all the bits, just like this. That will give us 1, 1, 1, 0, and then you add 1. Okay? 1, 1, 1, plus a 1 at the end. So immediately we came up with negative 1. And this works in both ways, actually. So if you want to go from negative 1 to 1, you can do that too. Start with your negative 1, flip all the bits, 0, 0, 0, 0, add 1, 0, 0, 0, 1. So you've just made negative 1, positive 1 again. So that's pretty nice. That's how your computer's doing it. So to negate a number, you just flip all of its bits and add 1. And that will give you the correct binary form of it. Are there any questions about that? It's an interesting little process. The reason it's called 2's complement is because flipping all the bits gives you what's called 1's complement. I don't know why it's called that, though. But you add another 1 that gives you 2's complement. So that is negative numbers in a nutshell. Now that we know how they're stored, we can manipulate the bits of any arbitrary integer. So let's do that. The first bitwise operator I want to teach you is bitwise AND. So we know what AND is, right? The logical AND operation is 2 ampersands. This is essentially going to do that just on individual bits of a number. It's going to look a little weird. And the operator for bitwise AND is, instead of 2 ampersands, it's a single ampersand. So I'm so sorry. You know that ampersand by itself means, in the type, it means reference. Outside of a type, before, it would mean address of, if you gave it a variable. And now it also means bitwise AND. It's disgusting. But now you know. So, yeah, let me kind of motivate the reason to have bitwise operators, and then I'll teach you bitwise AND. Okay? So, sometimes we have a number, and we don't really want to store a number in that number, if that makes any sense at all. Sometimes it's nice to store things other than numbers inside of ints. For example, if I had a 32-bit number, I could store 32 Boolean variables very compactly, right? They're all right next to each other. And so you could have some very long number, 1, 1, 0, 32 of them. And you could look at each bit and you're like, all right, this bit means, like this is a video game or something. If this bit is set to a 1, that means your character has an extra life or something. I don't know, have extra life. And if this bit is a 1, it means your character is currently riding a horse. Something involving the video game. I don't know. But do you see how you could like compactly do any Boolean value? Isn't that cool? Maybe you only wanted to store like a bunch of 4-bit numbers. There is no type in C++ that stores 4-bit numbers. But you could store a bunch of 4-bit numbers if you put them all right next to each other in an int. That's another thing that you can do. Okay, so there's a lot of things that you could do that are not available to you unless you manipulate the bits of a number. Okay, that's where I'm going with this. And now I want to teach you how to do that. All right, so there are ways to do things with individual bits of a number, like get the 12th bit, set the 3rd bit to 1, all those cool things. So let's figure out at least the first step to doing that. One of the operators is bitwise AND, and that's going to help us with extraction. So bitwise AND, what it does is it performs the Boolean AND operation, that double ampersand thing that we know, on each bit of a number. All right, so this is a little weird. You give it 2 numbers, first of all. So bitwise AND takes 2 numbers. Like here, let's pretend we're in 4-bit land instead of 32-bit land again. 1, 0, 1, 1. And let's bitwise AND that, so a single ampersand, with 0, 1, 1, 0. All right? And the second you ask C++ to go and do this for you, it's going to line up the bits of the numbers and look at each of them like this. It looks at the 1 and the 0 together. It looks at this 1 and 1 together. It lines them up. 0 and 1 together. 1 and 0 together. And it performs bitwise AND on each of them and gives you back a new number because of that. All right? So 1 is true and 0 is false, and then it does logical AND on each bit. So this, what's the result of this? Well, the 1 is true, and it's logically ANDing it with the 0, which is false. What's true ANDed with false? That's just false. So the answer in that bit is going to be 0. Does that make sense? That's what it's going to do for every bit. This is true ANDed with true. That's true. Cool. We get a 1 there. This is false ANDed with true. That's false. This is true ANDed with false again. That's again false. So our result is 2. 0, 0, 0, 1, 0. It doesn't really make sense in numbers, but it makes sense when you're dealing with individual bits. Right? So this was like, what, 8, 9, 10, 11. This was 11 bitwise ANDed with 6, 4, 5, 6. So that was 11 decimal ANDed with 6 decimal. That gave us back 2. It's a weird operation. It gave us back the number 2. But it did weird stuff with the bits. It makes no real sense to think of it in terms of actual numbers. But that is the idea. Okay? So, yeah. 1 is true, 0 is false. Bitwise AND uses that ampersand operation. In addition to references and address of, it's just kind of from context. You'll discover which one's which. And bitwise AND, what it's good for is extracting bits. Like, I want to know, hey, is bit 3 set? You can use AND for that. Let me show you how. So let's pretend that this is the number that I want to know if its third bit is set. Bit numbering, by the way, starts with the rightmost bit. This one is bit 0. This is bit 1. This is bit 2. This is bit 3, and it goes onwards until bit 31 if you're in an int. Okay. Let's say I wanted to know the third bit of this number. Like, I wanted to know, hey, is this a 1 or a 0? Obviously, writing it, we know it's a 1, but inside of a computer, like, we haven't looked at it yet. We're not sure. Here's how you figure out whether or not it's a 1 or a 0. What you do is you AND it with this special number where only the third bit is set. You put a 1 here, and you put zeros everywhere else in the number, and then you AND. All right? And watch what happens. The zeros, because we're ANDing, right? They force every number to go to 0. Every other bit goes to 0. Does that make sense? So this becomes a 0. True and false becomes false. True and false becomes false. False and false stays false. The only number that has the potential to be a 1 is that bit we cared about. And do you see how, if it's a 1, I'm going to get a 1 here. If it was a 0, doesn't matter that this one's a 1, it's going to be a 0. So there's your if statement. If the resulting number, by ANDing with the number where only the third bit is set, third bit set only, if that result is non-zero, the bit was set. Otherwise, I mean, it's going to force every other bit to 0. If this one was also a 0, ANDing with a 1 here does nothing. It keeps it 0, so the whole result is 0. And that's how you can tell if that particular bit was set or was not set. Other questions about that? That's a bit weird. It's a new idea. But that's how it works. And so this was apparently, again, going to number land where it doesn't make sense. This is, again, 11. And we're ANDing that with the number 8. And we're getting back the number 8. Interestingly enough. All right, and it's not 0, which means that bit was set. Are we ready for me to try this in code? I mean, there's nothing really extra for me to say in code. It's just I'll give you these same examples. I'll show you the syntax. So yeah, here we go. Cout. What was it? 11 ANDed with 6. That's 2. Cout 11 ANDed with 8. That's 8. And this one was extracting bit 3, right? So because the result wasn't 0, bit 3 was set. So we'll notice that. Yay, so we get 2 back and 8 back. And this one, that one was special. It's because this is not 0, then I know that bit 3 was set. If I made this the number, what was it? What's 0, 1, 1? That's just 3. If I made this the number 3 and I tried to AND with 8, trying to extract the third bit, the answer is going to be just 0, which means that the third bit was not set. All right. So yeah, that's the syntax, just an ampersand. And it does the Boolean AND operation with each individual bit of those numbers just lined up where 1 is true and 0 is false. All right, that's bitwise AND, good for extracting bits. The next one is bitwise OR. We know AND, we know OR now. OR is, in logical land, 2 pipe characters, and so in the same vein as bitwise AND, we chop off one of those, and bitwise OR is just a single pipe character. Okay? And what it does is it lines up every bit and performs logical OR on each of them, right? Remember that OR gives back true when at least one side is true. So, I don't know, here's my next example. 1, 0, 0, 1. Let's logical OR that with, it's supposed to be a single pipe character, bold. Let's OR that with the number 1, 1, 0, 0. All right? So what's going to happen is it's going to line up every bit, and it's going to perform logical OR on each of them. So for example, this one, it's going to look at 1 and 0 and see true and false, right? So it's going to OR them together. What's true ORed with false? Well, one of them was true, so the whole thing's true. That's true. Yay, so the resulting bit in this position is a 1, right? What's false ORed with false? Still false. What's false ORed with true? That's true. What's true ORed with true? That's still true. Perfect. So the result is 1, 1, 0, 1. And again, if we're thinking about this in number land, it doesn't make that much sense to go there, but we can do it anyway. This is 8 plus 1, that's 9. 9 base 10. And this is 12. 8 plus 4. So we're ORing 9 with 12. And getting back, weirdly enough, we're getting back 13. So it doesn't make a lot of sense, but it's working on individual bits. Okay? So bitwise OR is really good for setting bits. It's kind of like the opposite of AND. AND was good for extracting bits like figuring out, hey, was bit 3 set, was bit 40 set, if I have that many bits in my number. Bitwise OR is good for setting a bit. Okay? So for example, let's say I have this starting number, like 1, 0, 1, 0. And remember the bit ordering. This is bit 0, this is bit 1, this is bit 2, this is bit 3. Let's say I really wanted to set the 0th bit of this number. What could I do? Well, I can just OR it with the number that is a 0 everywhere but the bit I care about setting, right? Because that'll preserve that value there. And then put a 1 in the bit I really want to set. So this is the number where only the 0th bit is set, which is the number 1. 0th bit set only. And now the resulting number after doing the OR is every bit that was in the original number is preserved, like 1 ORed with 0 is still 1, right? True. 0 ORed with 0 is still 0, still false. So these are all preserved. And then the one that I cared about, I put a 1 here to force it to be a 1. Because anything ORed with true is still true. Okay? So now I forced there to be something there. So essentially this was so number 8 plus 2, so 10. 10 base 10. We ORed that with the number 1. And we got 11. Which, again, doesn't make a whole lot of sense. It's like addition somehow? Weird. But no, we were setting the 0th bit of the binary version of this number. That's what it's doing. So let's go to code and look at that. See out, what was it? 9 ORed with 12. That was the first one. Just a single pipe character. And then the second one was 10 ORed with 1. So set the 0th bit. And the resulting numbers, when you think about them in binary, it makes sense, but in decimal land, maybe it doesn't. we get 13 and 11. All right, so that's bitwise OR. It's good for it's good for setting bits, and is good for extraction. Any questions about that one? All right, you know that there's and OR in our language. What's our other logical operator that I haven't done yet? It is not. We got to do bitwise not now. Another name for that is complement. The exclamation point is how we do logical not negation, right? There's not two of those, so we can't like get rid of one. So there's a new operator for this one. It's just the tilde character. The tilde character flips all the bits of a number, and that's what not does. Like it's working on each bit. What's it doing? It's negating them. It's negating every single bit. It flips them all. True becomes false. False becomes true. So for example, and this is not a binary operator for once, in the sense that it takes two things. This just takes one number. It's a unary operator. But of course it works on the binary form of a number. I say tilde 1001, that's going to flip all the bits, perform negation on each of them. So 1 becomes a 0, 0 becomes a 1, 0 becomes a 1, 1 becomes a 0, so the resulting number is that. And this was like, I had 9, base 10, and then it becomes 6, apparently. That's the idea. So that's bitwise not, how do I want to do this? Let me show you, I guess first, let's just do this one in code, because an interesting thing is going to happen. Notice that this is not 4 bits. This is a 32-bit number. We're using ints right now inside of C++. So if I tried to bitwise not the number 9, print it, the result is -10, which is extra interesting. And that should make sense in terms of the 2's complement form. But what I was doing, remember what 9 is? 9 was 1001, and I said, please negate that. But it was not just 1001, it was a bunch of zeros over here, right? 32 bits long in C++. It was a 32-bit number, and I said, negate all of that, please. And so what it did was it put a ton of 1s down here, which if we weren't using negative representations, if we were using unsigned ints, that would make a giant number. But this is going to make a negative number for us, because we give away some of our large numbers to make negatives. And this ends up being 0, 0, 0, 1, 1, 0 at the very end, but a bunch of 1s at the start, because there are a bunch of zeros at the start of 9. Does that make sense? And so this was really the encoding of, if you flip all the bits of 9, it really gave you -10. Which makes sense, because the 2's complement form is flip all the bits, that's this, and then add 1. That would have made -9. Isn't that cool? So before we get there, we're going to make a negate with 2's complement function. Like instead of using the negation operation, we're going to do it from scratch with the not operator and then the plus operation. And I also want to use a makefile, just for fun, just to get us practice with it. So let's make a makefile for this one program, so that we can just say make and it will run and get compiled. So I'm going to make a new file called makefile with a capital M. There we go. And the name of the thing that I want is, I guess I'm just calling it bitwise. And in order to create it, I need bitwise.cpp. What I do to make the bitwise executable from bitwise.cpp, I do g++. bitwise.cpp-o bitwise. No need to go to a .o form if it's just one file. Just go straight to the final executable. And so now I can just say make. And it compiles my bitwise program because the first rule is the default rule for make. I could have said also make bitwise, but the first rule is the default. Perfect. So is that coming back to us? Any questions about this rule? So now we have a make file for our lovely programs that we're writing. All right, so now I want to make a 2's complement program. It'll be very fun. Because what was 2's complement? It was To negate a number, flip all the bits and then add 1. That's the 2's complement form of a number. So let's implement that. Let's make a negate with 2's complement function. Takes a number, gives back a number. Int negate 2's complement. And it takes a number, and it gives back the negated form of that number. Right? Returns negative n using 2's complement, because that's what we know now is how we store our negative numbers. That's the form that it's stored in. So return, flip all the bits of n, till the n, plus 1. So now we can call that. We can say, all right, cout negate 2's complement of 9. And of course it's going to return negative 9, but in the cool way that we know how. Now I can just say make to compile it too. ./bitwise, what do you know? Negative 9. So it goes up here, oops, up here with 9. It's like, all right, flip all the bits, add 1, that makes negative 9. So that's one thing that complement is good for. All right, any questions about any of that? So we learned and, or, and not. Because now I have a question for you. Maybe I'll give you these slides on Discord or something. But here's what I want you to try. I'll give you a few minutes to try it. Write code that unsets the 5th bit of an int. Call the int x. So let's say that, I don't know, let's say that x, for example, is, how do I want to do it? Let's say that x, for example, is this number. 1, 1, 1. How do I do it? 0, 1, 0, 1, 1. So that's my original number, that's x. And where's the 5th bit? It starts here, 0, 1, 2, 3, 4, 5. Here's the number that I care about. I would like to transform this into the number 1, 1, 0, right? That got flipped. That got unset, not flipped, sorry, unset. 1, 1, 0, 0, 1, 0, 1, 1. And it should have still worked. Like if this was already a 0, it shouldn't have mattered. Like it would just keep it a 0. Okay? So you need to write a program that'll do that. Okay? So how would you do it? So you want to set bit 5 of your number x to a 0 no matter what, and don't touch any other bit. Keep them all. All right? And so you can really do it in 2 lines. Like here's your int. Just give it a value, and then you'll say x equals blank, and that's all you need. So you can do it in 1 line, really. And here are my hints for you. You can do it with a not plus an and in some order. Okay? And my hint 2 for you is extract every bit except for bit number 5. Okay? So I'll go in Discord and give you those previous slides if you want to look at them. But that is your challenge. I'll give you a few minutes to think about that and help your neighbors. Unset the 5th bit of an int named x using bitwise not and bitwise and. I'll give you those 2 slides. Whenever Discord decides to open, of course. You can do it. It's trying so hard. And so this x is arbitrary. It could have been from the user. That's just an example. It should look the same for any number. Is it open? Still not. Okay. I'll at least prepare by copying this. Yay. Screenshot 1. Screenshot 2. and then I will be closing Discord. Alright, so take a few minutes to try this, see if you can figure out the trick. Take a few more seconds to try it, but I told you how to extract a single bit, right? How would you extract a bunch of bits? All but one. Would you extrapolate what I said? Alright, so let's pretend that was our example number, like that was x, whatever it was. It was 1, 1, 1, 1, 1, 0, 1, 0, 1, 1. Did anybody figure out, like, can anybody explain to me, like, if I told you, if I gave you a hint and said that and was the last thing to do, how could you, and this was bit 0, 1, 2, 3, 4, 5, and I wanted to end up with 1, 1, 0, and the rest was the same, right? 0, 1, 0, 1, 1. Only these ones changed. The rest were preserved. What's the number that I should be anding with? There's only one option. That makes the most sense, at least. Like, what's forced to go in bit 5, first of all? What digit? What bit? It's got to be a 0. What about these ones? Like, how would this one keep the ones around? The rest could be ones. Do you see how if you put a 1 in that position and use and, it preserves the value that was there? If it was a 1, it stays a 1. But I'm going to put 1s everywhere else. 1, 1, 1, 1, 1. And if it was a 0, like it keeps the 0 anyway, no big deal. But if it was a 1, now 2 1s make a 1 because we and them together. Do we see that? Does that make sense? So the secret number that I wanted to and with is the number with only bit 5 unset. Everybody else is set. Okay? How can I generate this fancy number with a bunch of ones everywhere except for one spot? The trick is to use negation. Then you have to deal with each individual bit. What is this but the negation of the number with just a 1 here and a 0 everywhere else? Do you see that? That's the number you can come up with and generate it pretty quickly. Okay? So this number, you can get it by negating you can achieve this number down here by negating a number with the 1 right here and a 0 everywhere else. That's 0, 1, 2, 3, 4, 5. Then a bunch of zeros everywhere else as well. 0, 1, 2, 3, 4. So that's bit 5. Make a 1 there. And then just negate that, because that'll put a 1 everywhere else but that place, and put a 0 right there. Does that make sense? That's how I can generate this fancy number that I want to AND with in the very end. Any questions about that? Is that what we came up with? So that's the answer. And what is this? This is, well, this would be the 2 to the 0's place, 2 to the 1's place, this is 2 to the 5's place, 2, 4, 8, 16, 32. So this is the number 32 negated. And that's how we come up with that one. Any questions about that? That's pretty cool. That's how you can unset a bit. Use an AND and a NOT. And so secretly, the answer is X is whatever the user gave you or whatever. And then X becomes itself ANDed with negate 32. Otherwise not 32. That's the one-line answer. That's how you'd code it as well. Do you have any questions about this, or are you ready to move on to a new operator? All right, next one. Let's do bitwise exclusive OR. XOR for short stands for exclusive OR, and let me teach it to you by showing you the difference between it and regular OR. Okay, so regular OR, which is technically called inclusive OR, it works like this. You have two numbers and you OR them together, X ORed with Y. Here's like the truth table. So if you OR together two trues, you get true. Anything with a true in it, in fact. True, false, false, true. Those are all true. The only time you get false with a regular OR is if both of your inputs were false. That's the only time you end up with the false at the end. Exclusive OR works like this. Let me make some room for myself. Oh, don't want to do that. There you go. Exclusive OR. You give two numbers, X and Y, and you do XOR on them. X ORed with Y. Exclusive ORed with Y. Here's the difference. True, 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 false, false, true, false, false. Exclusive OR is the same for all of these. True, false, that's true. False, true, that's true. False, false, that's false. This is the one place where it differs from normal OR. It says that true exclusive OR with true is false. That's the one difference. Exclusive OR. So regular OR is called inclusive OR. It gives back true even when both sides are true. But exclusive OR is like exclusive. Only one person gets to be true for my final answer to be true. Okay? So exclusive OR is true only if exactly one of the sides is true. Only one person gets to be true. And that answer makes it finally true. That's what exclusive OR does. And I guess you technically have a bitwise, or you have a logical operator for exclusive OR on bools, just like you had double ampersand for AND. It's like two pipes for normal OR. technically exclusive OR is not equals in bool land. It's true if they're not equal to each other, if they're different. That's what it's doing. But the bitwise OR operator is the caret character. And so this is why I had to like yell at you at the start of class, very beginning of the semester. Like, this does not mean to the power of. It's going to give you a very weird result, and now you finally get to know what that weird result is. It does bitwise exclusive OR on the bits of a number. So, all right, here's my example. 1, 0, 1, 1, exclusive ORed bitwise with 0, 1, 0, 1. So the answer is going to be, well, this is 1 exclusive ORed with 1, which is false. So 0 there. These two are different, so a 1. These two are different, so a 1. And these are also different, so a 1. Okay. The idea, so this was what? Let's see. 11? 8, 9, 10, 11. Okay, so that was 11, base 10. Exclusive ORed with 5? Yeah, 5. 5 base 10. And that gave us 14? Yeah. 14. Again, makes no sense, but that's how we can at least program it. Whee! So it was 11. Exclusive ORed with 5. And we ended up with 14, apparently. Boop. And so that is the character for that. So it's definitely not to the power of, right? Something very different. Nowhere near what that answer should be. So now you know. One thing that exclusive OR is really good for, you'll have to really wait until either CSCI 26 or CSCI 45 to fully understand the power of this, like exclusive OR. But I promise you it's important. And one reason why it's important is because exclusive OR is kind of like addition, if you think about it. It's really doing 1-bit addition. And so, like, our computers are performing exclusive OR when we do addition on numbers, secretly. The CPU is doing exclusive OR. So, like, 0 exclusive OR with 0, that's 0. That's the same as 0 plus 0. Ooh, 0 exclusive OR with 1, that's 1. That's the same as 0 plus 1. Same with the flip. 1 exclusive OR with 1, that's 0, which is correct for 1-bit addition. There would be a carry involved, right? That's kind of cute. So exclusive OR is kind of like addition. That's one thing that's used for inside of a CPU. It's secretly doing addition with exclusive OR, and then worrying about the carry and propagating it. A bunch of circuits. But that's what exclusive OR is all about. Questions about it? Because my next few slides make your life a lot easier. So, like, we had to do a lot of math. Like, this was the number with bit 5 set. Okay, let me count on my fingers and discover that that is 32. This is the number with bit 3 set. That was 8. I had to do math. This was the number with bit 0 set. That was 1. Not too hard to remember, but again, it could have been any bit set, and I would have had to calculate that. Let me show you a trick to never have to do that calculation yourself. It's called a shift. Bitwise shifting will make our life so much easier when we're trying to pick numbers to do bitwise operations with, right? So here are the bitwise shift operators. You have 2 less thans for left shift and 2 greater thans for right shift. These are the original operators that were in the C language that IOStream took and overloaded. So, like, really, this was the left shift operator, and cout just loaded it so that it looked like an arrow. Really, it was created to do bitwise stuff. Now you know. And yeah, left shift, for example, adds zeros to the end of a number. So, for example, it makes most sense with this example. 1, 0, 1, 1, for example. Take that and left shift it by 2, what that does is it brings in 2 zeros here. Boop, boop. It like shifts over the bits left by 2. And it brings in space for 2 new bits. And this becomes 1011, then it shifted it left, right? So it's got some new space here for 2 zeros. That's what it becomes in binary. Okay? So this was what? This was 11 base 10. We shift it left by 2 bits, and it becomes, oh gosh, this is 1, 2, 4's place, 8's place, 16's place, 32's place. 32 plus 8 is 40, that's easy. 4, so 44. It becomes 44 base 10. Do we see a pattern here? What did we just do to good old 11, making it 44? What's another operation that can give you 44 from 11? Yeah, we multiplied by 4 by doing shifts, by adding zeros. That is the trick. So we just essentially did 11 times, this is 2 squared. That's where that's coming from. 2 squared because we shifted by 2. That gives me 44. So, yeah, left shift, if you have a number and you left shift it by some amount, that gives you back n times 2 to the n. That's something that you can remember. First cool thing. Let's see. For example, again, if you had 0, 0, 1, 1, that's 3 in binary, right? And if we left shift that by 1, that gives me, I guess I'll do it down here again. That gives me 0, 0, 1, 1, and then it brought in a new place for the 0. And so that made, this was 3, this is 6, right? And the reason we got that is it was 3 times 2 to the what? 2 to the 1. So back in the day, CPUs used to be able to shift faster than they could multiply. And so if you ever multiplied a number by 2 in C++ on older processors, it would transform that into a shift by 1. Because it would do it faster. Because it's the same operation. That's kind of cool. Cool knowledge. So it's another way to multiply by powers of 2, which is nice. It's not the only thing that it's good for. I'll show you more on the next slide. But to go along with left shift, of course, there's right shift. So right shift shifts bits to the right, which like gets rid of them, right? Gets rid of the ones over on the right. Just like left shift technically is getting rid of bits way over on the left. So if you had a large value, it would mess with it. This one will mess with small bits. Let's see here. How do I want to show you this? Let's say we have the number 5, because it does different things. Right shift does different things if it's a negative number, and I just want to highlight that. So let's say we have the number 5, which is 101 in binary, and it's got a bunch of zeros to the left of it because it's just positive. That's 5. And let's say we right shift it by 1 bit. That's going to chop off this 1 and bring in a 0 here because it was positive. Okay? So that gives me back 1 0 at the end here, and then just a bunch of zeros. We brought in a fresh 0 right here, essentially. And what that does is it divides by a power of 2 if you right shift. So 5 divided by 2 to the 1, which gives us back 2, 1, 0. Integer division. Again, this was faster back in the day than doing actual division inside of our CPU. So translate division by powers of 2 to shifts, which is fun. If you do right shift on unsigned ints, it always brings in a 0 like this, or if it's a positive number that you're right shifting, it always brings in a 0. If you have a negative number and you right shift it, it will preserve the negativity, so that actually does the correct division. It will bring in a 1 instead. The trick to knowing if you have a negative number inside of your programs is check the very first bit, or from the left, that is. So like the 31st bit, check that. Where is that? If it's a 1, it means it's negative. If it's a 1, it means it's negative. Those are the ones that we have like taken away from being giant numbers. If your 31st bit is a 1, that means it's a negative number. So it just preserves that if you right shift. Not a big deal. That's all that I really wanted to say there. a very, very nice thing that you can do. Do I want to do this now? Okay, let's do these examples first. So what did we just do? We did 11 left shift by 2. Oops. And we did 5 right shift by 1. Not 5. And that gave us 44 and 2. All right, so that's the syntax. But another thing that shift is good for that you usually use it for, besides you don't really do it for multiplication or division purposes these days, you just hard code the number and use multiplication. You can use shifts to get that number, that special number that you wanted to AND by, that you wanted to OR by, to extract a bit, to set a bit. That's really what shifting is awesome. For example, let's go back to like AND. Let's say, I don't know, I wanted to extract this bit number 3. 0, 1, 2, 3. So I wanted to know, hey, is this a 1 or a 0? So I'm going to AND, right? I'm going to AND with the number with a 1 right there in that bit that I care about and a 0 everywhere else. And that'll give me back 0 so that I know it's not set. But how can I easily get this number? With a shift, it's so easy. It's just, well, start with 1. That's the number with the 0th bit set. Shift it left by 3, because that'll make a number with just bit 3 set. And so I don't have to do weird hand math to calculate the, okay, that's the number 8. Just AND with 1 shifted left by 3. It's beautiful. Isn't that nice? If you want to set a bit, 0, 0, 1, 1, if I want to set bit 3 of that one, 1, 0, 0, 0, right? You OR it with the number with just that bit set. And it preserves everybody, and it sets that one. And again, that's 1 shifted left by 3. Isn't that cool? Because the reason it works, right? 1, that's the number 1 in binary. It's just a bunch of zeros and then a 1. And you left shift it by 3, which means bring in 3 zeros over here. Start moving it over, shifting it over, and it brings in a 0. 1 0, 2 zeros, 3 zeros. And so now you don't even have to think when you do your operations. You're just like, all right, I want to extract. What are all the things? Let me split this. What were all the things that we were doing before? Up here, it was like, all right, I wanted to know bit 3 of 11. Was that set or not? Watch. Instead of saying 11 ANDed with 8 to extract bit 3, just be like, all right, 1 left shifted by 3. That's the number I care about, right? That will set the bit. Okay? That's the one I want. Alternatively, if I want to know if bit, or if I want to ensure that bit 0 is set of the number 10, I can take this again, boop, and I can, like, calculate the number. Well, this one's easy to calculate. It's just 1 shifted left by 0. But that's the number with the 0th bit set. And so you can do this arbitrarily. You can make a function that checks, hey, is bit I set? And you can just shift 1 left by I. That's one way that you can do it. All right. Let's preserve these comments over here. I think that would be helpful. So that's one thing that you can fix. Now, if you want to check a bit, you don't have to calculate some weird power of 2. You can just shift 1 left by whatever you care about. Okay? That's the idea. Are there any questions about that? That's a fun little example, I think. Because I have one last question for you. Here it is. Dun, dun, dun. I would like you to try to write some code that toggles the 4th bit of an integer called x. All right, so for example, let's say that here's our starting number, 1 0 1 0 1 0. So this is bit 0 1 2 3 4 5, and I want you to toggle bit 4. So if it's a 0, I want you to make it a 1 and preserve the rest of the number. So 1 1 1 0 1 0. And then if you gave this number to your algorithm, to your code again, then you'd take this bit 4 and you'd toggle it back to a 0. 1, 0, 1, 0, 1, 0. Can you think of how you might do that? It is also possible to do it in one line, but you can think of it in whatever order you want. You get some arbitrary number from the user. You need to go into it and update the number to be that same number with bit 4 toggled. If it was a 1, make it a 0. If it was a 0, make it a 1. Can you think of how to do that? It doesn't have to be in one line, but I want you to think about this in terms of the stuff that we learned today. So give that a try. A few minutes. Can you discover the secret? That one. Okay, I'll remember to do that. A few more seconds to think about it or try it, and we'll talk about it. All right, do we have any good ideas? Anybody figure it out? How could you toggle a bit? Figure out the one-line answer? Because like the way that you would know how to do it, right? The way that's not tricky would involve like, all right, let's extract every bit of this number, or I guess what I should say is let's take this number and extract the fourth bit. See if it's a 0 or 1. You can have an if statement, right? If it's a 0, then I'm going to make it a 1. Otherwise, I'm going to make it a 0. And you know how to do both, right? You know now how to put a 1 somewhere. That's, you just OR, right? Put an OR in this position, in that location. You'd OR with it if you noticed that it was a 0. Or if you want it to be a 0 and because you noticed that it was a 1, you could use this answer. the one that you came up with. You would extract every bit without, except for that particular bit number. So that would be a several line answer, but there is a trick, and the trick is exclusive OR. Watch. So let's say that here was your starting number, 1, 0, 1, 0, 1, 0. If you exclusive OR with the number with bit 4 only set, 0, 1, 0, 0, 0, 0, look what happens. Everybody else is preserved because a 1 exclusive OR with a 0 becomes a 1, and a 0 exclusive OR with a 0 stays a 0. So everybody else is preserved, but if these differ, it becomes a 1, right? And so that correctly does it for that one. And then we could try this one, make sure it does it the other way too. 1, 1, 1, 0, 1, 0. If you exclusive OR that with that same binary number, it will again preserve everybody else, 1, 1, 0, 1, 0, and then toggle this one. Because if there are two 1s, it makes it a 0. Ooh, that's pretty cute. So that's the answer. You would do X, and what is this number? Like, how would you calculate this number using shifts? Very easy. So therefore, we should XOR with the number with bit 4 set. You don't even have to think about calculating that. Just be like, all right, 1 left shifted by 4. Whatever that is, that's the right one. So take X, exclusive OR it with 1 shifted left by 4. That's the quick version of the answer. But you have enough information to do it the harder, longer way if you need it to. Okay? Any questions about that example? All right. So for my final slide, I just want to tell you why you should care if my original example was not good enough for you. Like, what was it? The video game example, or like packing a bunch of numbers that are small together. Like, maybe that doesn't float your boat. So here's like a real reason why you would really want to do binary bitwise manipulations. So the best example I could come up with was if you're making a compiler. Like, you're making C++, eventually you'll take a compilers class if you're a CSCI major. You have to generate binary. A program gets loaded in memory, and it is a binary thing. You have to generate the exact machine instructions for your program. Okay? They're just fancy long numbers that represent, oh, please add these places here. Please call this function. Okay? There's a bunch of special bit stuff going on there, and you'll have to set those bits in a certain way to achieve that particular instruction that you care about emitting at this point in time. So let me show you that. It'll be fun. So here's my compiled program. It's called Bitwise. There's a special, first of all, look, if I try to vim Bitwise, we've all tried this, right? And we get garbage. This is machine code. This is binary 1s and 0s. That's the processor's, it's the language that the processor is able to understand, not us humans. But there's a program called objdump, and it has a -d option for decompile, or disassemble, I think, bitwise. And what that does is it takes the machine code and extracts back out the actual CPU instructions. So let's take a look at that. Here, where's the main function, first of all? That's start. That's not even main yet. Did I already pass it? Come on. There's main. Cool. So, here's me doing stuff in main. Let's see if we can find any of our exact instructions. A lot of this is cout, unfortunately. Let's see. So it's building stuff. Yeah, I can't quite find it. It probably got optimized away anyway. But look, let's say this. There are a bunch of instructions. These are CPU instructions, by the way. You'll have to wait till CSCI 45 to fully understand them. But there's a bunch of instructions that start with MOV. That stands for move. And they're moving different things around in different places. Like, here's the number 2 being moved somewhere. Here's some things being moved between each other. Look at how all of those instructions, like here's their binary form. This is hexadecimal, by the way. You can extract binary out of that. But this move starts with 4889, but then it ends with E5. This move starts with 4889, but ends with C7. This move, they all start with 4889, so you have to put that in your instruction if you're writing a compiler. And then you figure out like what are the things that are being moved around between each other, and then you encode those in the last final byte. So you have to pick the correct bits that represent RAX and RDI versus RDX and RSI. All those things. That's one good reason to learn bitwise operations, because one day you'll have to emit instructions. Write binary stuff. That's one example. And then also, like if you have an image, all of your image files, if you want to read those, not the cute example that was text-based that I showed you in class, but like a JPEG, for example, that is binary encoded in a very special way. It's like the first few bytes have like a header for the file that tell you like how wide and how tall the JPEG image is, and it tells you what colors are inside of it, and then it gets to the actual pixels that you can then go and extract. Okay, so if you want to read an image, like you double click it on your computer, somebody wrote a program to go and read the bytes and extract the bits in a way to understand what is the size of this image that I'm about to display for you. Where are the pixels so that I can put them on the screen for you to look at? Somebody's doing that. That could be you one day. Okay, so that is my motivation, just in case my silly motivation at the start was not good enough. Yeah, any questions about any of that? Okay, so yeah, that's all that I'm doing today. There will be a new lab next week, but not this week. So just work on whatever's already out. That is all that you have to worry about.